Okay, today we're going to be talking about equations of lines, and we'll find that linear functions are the most important functions in the world because they are the only ones in which the rate of change of the y-coordinate with respect to the x-coordinate is always constant. That is, we're basically on cruise control if you're thinking from a speed situation. These equations of lines you'll be seeing throughout the semester because we take advantage of the constant rate in calculus to find out what's going on when the rate is not constant, and we work with that over and over and over again. So you're going to be seeing the problem find the equation of the line over and over again this semester, and even beyond when you deal with something called the fundamental theorem of calculus, something that we talk about here will be the most basic situation in which that fundamental theorem turns out to work. To begin here, what we're going to do is first talk geometrically a little bit. We're going to ask here, what pieces of information do we need to know about a line to be able to determine the entire line? So from a geometric standpoint here, if we're given 2 points on the line, it's fairly obvious, and some might consider this to be an axiom of geometry, in fact, that if you have 2 points here, there's exactly one line that fits, that contains those 2 points. No other line contains both those points at the same time. And so it turns out the 2 points are enough to give us a unique line. Also, if we're giving a point and the slope of the line, which is basically the direction we could look at geometrically in which the line is going in here. If we're given the point, if we were just given a point alone here, we would have all sorts of lines that would go through that would contain that point over and over and over again. But you can see here, each of those lines has one specific direction here. And so if we gave the slope in addition to that information here, that would nail down exactly which of these lines that we wanted to talk about here. So it turns out from that point of view is that the point and the slope together will determine one unique line. On the other hand, if we were just given the slope of the line, and say that slope was 3 or 5 or some positive number here, that would not give us, just like just given the point here, that would not give us enough information to determine one unique line. In fact, we would have a family here of parallel lines here, all going in the same direction here. But what if we were given one point, one singular point on the line as well as the slope here? So we would know our line was one of these lines here. We want to know which one it was, or it might be some other parallel line that I haven't drawn. So if we were given a point here on the line, say this point here, we would know, since all parallel lines basically are selfish, they share no points with each other, we would know that only one of these lines here could contain that point. Pretty lousy line drawn there, but we'll live with it here. And so it turns out here, geometrically speaking, given both the point and the slope of a line here, we are able to determine one unique line. So now let's look at the problem algebraically, which is the way that you will be dealing with it in the future here. By the way, it's somewhat amazing here that just these small amounts of pieces of information, either the 2 points or the point and the slope, is enough to determine here an infinite number of points here. You get the whole family by just knowing those couple of pieces of information. Now let's go on and talk algebraically. First form of the equation of a line, which also determines all the points of the line, now numerically or algebraically rather than geometrically, we're going to go with probably the more famous y = mx plus b, the old slope-intercept form of the line here. And we're going to see where that comes from. And we're going to do that as well as finding other forms of the line, of an equation of a line, by meeting a friend named Freelance Freddy. And let's read the problem here. Freelance Freddy works a new job for a new hourly wage every day. He brings money for lunch, and as he works, keeps track of how much money he has, including his lunch money with a meter, maybe to keep his employers nervous. I don't know. First problem here about Freddy here. Today, Freddy flips burgers at Mickey B's Burger Emporium. He forgot to bring lunch money, so he has no lunch money today. He looks at his meter 5.3 hours into the job and sees that he has $47. We want to know how much money will the meter register at 7.8 hours. And then in general, how much will the meter register at X hours. Basically what we're doing here in all of this, when asking, for example, how much money will a meter register at 7.8 hours, we're finding out, can we determine any point that we would like along the line that would be representing the relationship between the number of hours Freddy works and how much money he has, including his lunch money. So let's solve this problem here. First of all, to answer how much money he'll have at 7.8 hours here, what we'd like to do is to find out what rate. It's quite natural, in fact, to ask at what rate is Freddy earning money each hour. To do that, we know that he's worked 5.3 hours and he has $47. Now, none of that $47 has anything to do with his lunch money because he forgot to bring his lunch money. His lunch money today is $0. And so that entire $47 came from his earning money over time here. So what we'd like to do, this is a division problem. And we have $47, and what we'd like to do here is find out how many dollars were devoted to each one of those hours here. So we take 47 and we divide by the number of hours, 5.3 hours here, or if you will, a fraction. And that turns out to be around, we're going to be very approximate here in this lecture here, $8.87 here in each one of those hours here. So $8.87 per hour. Now, to answer the question then is how much money will the meter register at 7.8 hours? Well, that becomes quite simple here because we have each hour here, we devote $8.87 and $8.87. And so all we need to do here is we want 7.8 copies of that $8.87. And so we would solve that here as the amount that he has at 7.8 hours here is going to be $8.87 per hour times 7.8 copies of that here. That turns out to be around $69.19. Now, we don't really care too much about Freelance Freddy. He's a nice guy, but we're not too concerned about finding his amount of money hour per hour per hour. What we'd like to do here, at least for this lecture's purposes here, is find the amount at X hours. In fact, let's call that another variable here called Y here. And what we would do here is do the very same thing we did in the numerical example. We would have now X copies of the $8.87 for each hour. And so that would be 8.87 times X. And so here we have a linear equation here of the form Y is equal to $8.87 per hour times X hours here to give us the amount of dollars there he has at that time, after working for that amount of time, I should say. Notice here that this is the most basic of linear equations. In fact, it's a very pure ratio here. And the most important thing is, just like geometrically, is we were given a certain amount of information here, and this $8.87 per hour is essentially what we called in school our slope, or our rate of change of dollars per hour here, per each hour here. Slope is a rate. No matter how you cut it here, it will always be some sort of rate, some sort of per quantity here of one variable, one quantity per some other quantity here. And here we see that given that slope, actually, and technically we were given a point on the line as well, in that case being 0, 0. When he worked 0 hours, he had $0 because he had no lunch money. We were able to find an equation that describes all points of the line x, y, and a formula to be able to find those points. So now let's try to look at a different scenario with Freelance Freddy. And we have here now Freelance Freddy is teaching math at OSU. And he brought $8.75 in lunch money today. So we now know he has some lunch money. So at 0 hours, we know he has $8.75, so even before he begins his work. Now he looks at his meter 5.3 hours into the job and sees that he has $47. Remember, that includes his lunch money here. And the question is the same question we asked earlier. How much money will the meter register now at 7.8 hours into his job? And let's assume, I guess, for all these problems here, he never really uses his lunch money. He's so involved with his work. And again, we also want to know how much will the meter register in general at X hours, which is our major goal for this lecture. So now this is an arithmetic question. And once again, what we'd like to know is what is the rate at which he's earning his money? What is the slope of this situation? Since he's earning at a constant rate, what is that rate? And to answer that, we have that $47 there really has, part of that is his lunch money, and it really has nothing to do with how much money he's earning per hour. So what we'd like to do first here is let's just work with the money that he's earned over that time and knock out that lunch money out of the $47. So we subtract here 47 minus 8.75 here. And what we'd like to do with that now is to take that amount of money, whatever it might be, and divide that by how many hours he works. So this is the amount of money that he's earned over that period of time, and this is the period of time there over which he's earned it there. And if you take this here and crank this on your calculator, what you'll get is that he earns here $7.22 per hour on this job. So how are we going to use that here? Well, what we know is that his money comes in two parts. One is his lunch money, and one is from his earning $7.22 per hour. The question asks is how much will the meter register at 7.8 hours? In order to solve that, basically, what we can do is take part of that there is part of the meter, so the amount on the meter at 7.8 hours here. And once again, we can call that y if we'd like. How do we calculate that? Well, we can take, first of all, some of that money is his lunch money. And the rest of the money comes from his earnings here. So this is like the problem before where we had, okay, well, every hour he gets $7.22 or $7.22. And he's going to be working for 7.8 hours, goes by here. So we just need 7.8 copies of that. So that's a multiplication problem. And so we wind up with, if you crank this on your calculator, he has $8.75 plus $56.32 he's earned. So all told on his meter there, he's going to have $65.07. Well, now what we'd like to do here is find out, well, what about y in the amount on the meter at x hours? In other words, for any number of hours of working that we want here, can we predict how much money Freelance Freddy will have on his meter. Well, we do the arithmetic here to kind of give us an idea for what goes on in the algebra. It's a good algebraic thinking process. Do an arithmetic situation first, and then mimic that when doing the general case. So in this case here, well, we still have the $8.75 that he has to start with there. And then we're going to have X copies of $7.22 for each one of those hours that goes by. So that's going to be 7.22 times X. Or if you will, the Y here would be, using the commutative property, switching things around, 7 point of addition, that is, $7.22 X plus $8.75. And so now you see here is your slope times X plus the initial value here, and as we know, this was how much he had at 0 hours there. He had $8.75 at that point. This is basically your y-intercept if you were graphing the line there. So we have the slope and essentially the y-coordinate of the y-intercept here put together helps make the equation of the line to find out exactly any amount of money he wants at any time. In other words, it determines the entire line given the slope and the y-intercept. However, if you recall geometrically here, we didn't necessarily need the y-intercept to be our point to go along with the slope to determine amounts here, or determine the entire line here. We can find any old point as long as we know that and the slope, then we can find the line geometrically. So let's look at that algebraically here. Today, Freddie is now starting pitcher for the Cleveland Indians. He brought some lunch money, and we don't know how much lunch money he has. It's going to be a little bit mysterious for a while. And I'm kind of hiding the y-intercept from you here. Now he looks at his meter 5.3 hours into the job and sees that he has $478. He also then looks at his meter 7.8 hours into the job and sees that he has $700.50. Well, we know the major leagues pays a lot of money here, a lot more than teaching at OSU or working at Mickey B's and Burger Emporium. Without figuring out how much lunch money he has, so this is going to be very important here. We want to resist the temptation for finding out how much lunch money he has. How much money will the meter register at 9.34 hours? So again, we want to find out how much money will he have at some other time other than what's given here. And then later, how about at X hours here? Okay. And then when we're finished there, we'll do the same problem, but then we'll go back and find out his lunch money first. But for now, we're going to do it without figuring out how much lunch money he has. Well, what are we essentially given here? We're given two instances of the relationship between the number of hours and how much money he has. Essentially, geometrically here, we're given 2 points on the line, okay, that he's earning with a constant rate. Now, just like the other problems, though, it would be great and very helpful there to find out how much money he's earning per hour. Okay, this is not the same as lunch money, obviously, here. This is asking, what is the slope? Well, even without knowing any formula here, it's pretty, well, hopefully a little bit easy to see how we're going to figure that out. We know we want to only deal with how much money he's earning per hour there. Obviously, it doesn't have anything to do with his lunch money here. We know that at 7.8 hours, he has $700.50, and at another time, 5.3 hours, he has $478. Can we figure out how much money he's earned over that period of time? Well, sure. The amount of money he's earned, so the rate of earning here, or his hourly wage, is how much money he earned over that period of time. So that's going to be $700.50 and knock out $478. And notice here, by the way, that by subtracting here, this is the amount earned in that amount of time here. This difference here, whatever that number might be, is not going to have anything to do with his lunch money, because we know that his lunch money is somewhere contained within that $700.50, And we also know his lunch money is contained within that $478. When we subtract here, whatever that lunch money was in here and in here gets subtracted out. So all that's left here is what he's earned over that period of time. And how do we figure out how much time he earned there, or how much time he's taken to earn that much money here? Is, well, this was at 7.8 hours here, and we knock out the 5.3 hours from before, and we see that he's earned that amount of money over this difference in times here. Calculating this here, we find that he's earned, this will be $222.50 over a period of 2.5 hours, which winds up being $89 per hour here. Now notice here, we've just found the slope. And without even memorizing or knowing some formula here, it makes sense that to find the slope given 2 points here, we do the change of y over the change of x, which is something you've learned in school. Hopefully it makes sense. And hopefully it made sense in school, and if not, hopefully it makes sense now. Well, we still haven't solved the problem yet though. We want to know here, how much money will the meter register at 9.34 hours here, was our original question here. And all we have here now is our rate of change here, our constant rate, our slope of his earning here, 89 bucks per hour. We're not allowed to find his lunch money here, so all we can still work with is maybe those two instances that we already have. So for example, let's look at, take advantage here that, well, we don't know how much he has at 0 hours, but we sure know how much he has, say, at 7.8 hours into his job. And we know he has $700.50. We'd like to know, what about his situation just a little bit later from 7.8 hours? What about at 9.34 hours? So what we can do here is the amount, again, we can call this y like before, the amount of money at 9.34 hours. What we can do is we can say, yeah, we already know that he has $700.50 at some point in time here. We could do this, and we could take this amount of money here and just add what additional amount of money did he earn between 7.8 hours and 9.34 hours. Well, we know what the slope is. We know the slope is 89 here, and we want to know how many 89s will take place between 7.8 hours and 9.34 hours. Well, that's the amount of time between that amount between those two times there. How do we find that amount of time? Is by subtracting 9.34 hours minus 7.8 hours here. And essentially here we've solved the problem, because this is going to give us our starting amount, and then we add here how much it changed over the intervening hours between 7.8 and 9.34 hours, with $89 per hour given to us. So we crank that out just with arithmetic here on our calculator, and we get $700.50 for our start, and our change turns out to be $137.06 roughly. So putting the start plus the change together gives us our new amount of $837.56. And that solves the problem without finding his lunch money. Now notice here that we could have solved that same problem with the starting amount being what he had at 5.3 hours, which was $478. So let's figure out here, is this the same? So we're going to start with the $478 and add in, what about, we want $89 per hour, but now it's since 5.3 hours, not 7.8 hours. So we figure out how much time took place between then. And if you crank this on your calculator, I won't do it here, but you will find here it will be 478 plus the amount of change. So again, a start plus a change idea, you will wind up with the same amount. It makes sense because there is only one line that's going to contain these points in these slopes. We just happen to be working with a different point that time. Well, how much will the meter register at X hours? Well, we will just mimic the arithmetic here, and we can take one of the initial points that we want. Take your pick. We saw that both will wind up giving us the same point because we're on the same line. That will be here your starting value plus your slope times the difference in time here between X hours here and the time that we have. So that's going to be X minus 7.8. So we have a start plus change equation. And if you want, you can simplify that to get it to y equal mx plus b form if you'd like. We're not going to do that here, though, right now, because we're going to emphasize this form of the line, which is called, by the way, the point slope form of the line because it gives you the point 7.8, 700.50, and it also involves the slope. And from that there, you can find his amount of money at any time that you wish, as long as he keeps working. So now what happens in general? Well, if we're given 2 points on the line, so he's starting pitcher for the Indians again, and he brought some lunch money here, which we never did find. He looks at his meter X sub 1 hours into the job and sees that he has Y sub 1 dollars. And he looks at his meter X sub 2 hours into the job and sees that he has Y sub $2. Once again, how much money will he have without figuring out his lunch money at X hours into his job? Well, we would just mimic the arithmetic we did before. First thing we did was we found out at what rate is he earning money. That was our slope, often called M, which, by the way, comes from the word multiplier, because you're multiplying that by how many hours he works in various of these problems. And how do we find that? Well, we found out how much money he earned over the specified period of time that we're given here, and divide by the number of hours that he worked. And we know that from school, but now we know it from making sense. We're just going to call that M for now, rather than having to rewrite that quotient over and over and over again. Then, what did we do here to find out how much money he has at X hours here? Well, we took one of the initial values we had, say Y sub 1, and we added in how much it changed here. So this was like your starting amount, you might recall. And then we add here how much it changed. Well, how much did it change here? Well, he earns M dollars per hour. And we want to find here over how much time since that starting value here did it go. Well, that was however many hours you want, the X, minus the known number of hours, which was X sub 1. And this is called the point slope form of the line. You may have remembered this from school as looking at like this here, an equivalent form here is y minus y sub 1 is equal to m times x minus x sub 1 here. Basically here you're looking at it as the change of y here from the known value of y here is equal to the change that we've been talking about here. The amount of time that went by times how much money he's earning every hour. You may also have learned it by looking at it this way, y minus y1 over x minus x sub 1 here is equal to m. Basically what that tells you here is at whatever point xy you are here, when you calculate the slope from the known point, the change in y over the change of x, you'll always wind up with that same unique slope. Basically says any line only has one slope. Now you'll be using probably more often than the slope-intercept form, you'll be using this point-slope form of the line quite often here in Math 1151. Several different places. One will be finding what we're going to call the equation of the tangent line, and the cornerstone of that will be finding that slope, which is now going to be changing with functions there. You're going to be wanting to find what is the unique slope at any particular time, somewhat like taking the picture of your speedometer as you drive along there. Although that speed might be changing, you have a unique speed at any particular time there, and you're going to want to find the line that seems to be going along just like the function is at that time, and you'll be using the point-slope form of the line to find that equation. You'll also be doing that within linear approximation, which basically is the point-slope form of the line. And then also there you'll be using it within the fundamental theorem of calculus, and again where the slope is always changing, but we'll catch that when that comes up later in the semester. That would take a while to get through right now to talk about what that would mean. But yet you'll still be using this basic idea of let's start where we know and add on how does that change, and that's basically the theme of the point-slope form of the line. By the way, we did not solve one of the problems that I gave you here earlier about Freddie here. Let's look at that. It said when you are finished here, do the same problem, but now first by finding how much his lunch money was. So we're going to kind of cheat here. Instead of finding the point slope from the form of the line, we're going to work toward finding the slope-intercept form, because the y-intercept, if you recall, was the amount of money he had at 0 hours, which we call his lunch money. So how are we going to do that from this information here? Let's find his lunch money here, and just using basic arithmetic ideas here, and without delving into any formulas we memorized from school. In fact, we will find that we're going to do the exact same thing you might have done in school algebraically. We're going to do it with arithmetic. We know that he looks at his meter 5.3 hours into the job, and he sees that he has $478. He also looks at his meter 7.8 hours into the job and sees he has $700.50. Now obviously here we did figure out what his rate of change was of earning money was $89 per hour. So we know he's earning his money there at $89 per hour. We also know though from this amount of monies that are given here, say with the $478, let's just work with that for now. We know that some of that $478 was his lunch money, and some of it was the amount of money he earned over that period of time, the 5.3 hours. So let's figure out here his lunch money from just knowing that. So we know that $89 times the 5.3 hours there is going to give us how much he earned over that period of time. That turns out to be 89 times 5.3 is $471.70. Okay, so in that 5.3 hours there, of that $478, $471.70 was what he earned with the Indians. So that means the leftover part, whatever was left out of the $478, was his lunch money here. Well, how are we going to figure that out? Well, that's just subtraction. So $478 minus the $471.70 here turns out to be $6.30. Now maybe I should have rigged the numbers a little bit better. That's not going to buy him too much up at Progressive Field with the Indians. But he's playing anyway, so he probably gets that in the clubhouse. So we know that he's earned $6.30, or he has $6.30 when he comes onto the job there and earns money at $89 per hour. And so we know then, if we wanted to write this with the point slope form of the line there, we can rephrase the whole problem as he earns $89 per hour and he starts with $6.30. So his slope is 89. Kind of your y-intercept value is $6.30. and therefore the point slope from the line there, or the slope-intercept from the line, would be $89 x plus $6.30. Well, notice here, this process here that we just went through to find his lunch money here. And then, by the way, you can always solve the rest of the problems then by using the slope-intercept form now. So, for example, you could just plug in the 9.34 into this here and figure out what he has there. So he's worked a total of 9.34 hours at $89 an hour, and then you tack on the $6.30 he brought in for lunch. You're going to get the same answer we got before for his amount of money at 9.34 hours. But if you notice here, this arithmetic process you've probably done before when you said in school, I don't care about the point slope form of the line. I want the slope-intercept form. I know because he's earning $89 per hour, I know the equation of the line must be y equal 89x plus b. And I also happen to know a point on the line here. And so what did you do? Well, you often just plugged in the known value here of x, 5.3, in search of b here, and you then plugged in y equal to 478. And then what did you do to find b? Well, you just subtracted this amount from both sides here, 478 minus 89.5.3, which happens to be the exact same calculations you did before. We just calculated that product here, then we subtracted 478 minus that product, and that gave us the $6.30. Therefore, we know that is our equation of our line, and we can find out how much money he has at any point. And so by just reasoning here with arithmetic here, we can do exactly what you did way back when with algebra and find the slope-intercept form of the line. Which equation of the line is better to use? Doesn't matter. They're both representing the same line because we were given the same amount of information about it. We know geometrically given 2 points, we can find a unique line, or given the point and the slope, we can find a unique line. We just now done it algebraically, and now we've done it in 2 different ways. So when it comes time to find the equation of the line in calculus class, now you have a couple of different ways to approach it.